Hi everybody, welcome back. This is going to be our chapter 8, sections 3 through, through basically the end actually. I believe it's 3 through 9, which is the remainder of this chapter. We've done sections 1, sections 2, and I think sections 3 through 9 will go a lot more quickly than you think it will. So we talked about types of soil and what makes up soil, and then that was in section 1, and then in section 2 we talked about some of the hazards that that soil or really a soil subsidence can actually pose for humans, as it can change the shape of the land and so forth. Now we're going to be talking about in section 3 some of the regions that are at risk for some of these factors. So I'm not going to read all this stuff off to you. Some of these terms like karst topography and permafrost you've heard already, so I'm going to kind of move a little bit more quickly through them. But there are some of the places in the United States where you can expect to find some of these kinds of features, some of these types of soil subsidence that we've talked about so far. So karst topography, that's where we have, as you recall, land that is, or rock underground that is carbonate. And carbonates can very easily be dissolved by acidic groundwater, and so when that dissolves away and leaves caverns, it can collapse and create sinkholes. And so about 10% of Earth's surface is made up of karst topography, and a good amount of the United States, certainly more than 10%, 25% of it, is covered with karst topography. Tennessee, Virginia, even Pennsylvania. In fact, we're going to look a little bit later at where some of these regions are in Pennsylvania. And we actually do have some sinkhole regions in our state as well. Kentucky, Missouri, Arkansas, Texas, Florida, even Puerto Rico, which isn't a state, but it's, I believe, a territory. These are places where you can find karst topography, places that have carbonates in the soil that can be dissolved by acid, even weak acid. Permafrost, we talked about that, how that is areas of Earth's surface that are, if not permanently, at least mostly permanently frozen year-round. And it makes sense that Alaska and Canada and Russia have large amounts of permafrost. And of course, Alaska is the only part of the United States. Canada and Russia aren't, but it makes sense that they all are because they're well above the equator towards the north. Compaction of sediment. All right, wherever you have any kind of marine delta, you're going to have compaction of sediment. Any place there's organic rich soils. All right, New England, Washington State, Alaska. Think about those places. Those are places that are coastal and have access to moisture, and they're also fairly cold as well. And so these soils are going to be very organism rich, and organisms can play their part in breaking down soils as well. Coastal wetlands. Right here, Florida Everglades. You've probably heard of that, where much of that, I guess the lower part of Florida is a coastal wetland. Sacramento, I'm not sure how to pronounce this, San Joaquin, I want to say, Delta in California. And, you know, probably Louisiana is known for having coastal wetlands as well, as is North Carolina. These are areas where water affects how the soil holds together. Expansive soils, soils that expand because of water being present and causing clay particles to spread out. The western U.S. and Canada, even though pretty much all states have some degree of swelling clays, you've probably, if you've ever dug in the ground at all, at any depth, you probably come across clay. It's really heavy and thick and dense and not very easy for water to percolate through. Okay, frost heaving, all right? Alaska and much of the northern United States and Canada, all right, as the ground freezes, it heaves, it swells up because frozen water expands. And also finally, seismic related soil failure or soil subsidence. Alaska, we certainly have earthquakes in Alaska. Hawaii, we've got earthquakes and volcanoes. And of course, our Pacific Northwest is known for having earthquakes as well. So these are all areas that are affected by soil subsidence in one way or another. So this map right here is, of course, the United States, and all the green is karst topography. You can see in the middle of Missouri right here, and some of Arkansas, and all through, Texas and Oklahoma and Kansas, down into even New Mexico. Large amounts of karst topography. And remember, karst topography is formed because of carbonate rocks underground being dissolved by acid. All right. Well, the same thing that makes up carbonate rocks is the same thing that makes up oceanic shells of marine creatures. And it was believed that at one time there was an inland sea in what we now call the Great Plains. And so the carbonates that were left behind is very possible were left behind by all those shell deposits that were left from that sea. Shells, coral, all that is carbonates and is easily dissolved by acid. So that's the belief that these carbonate and now karst areas are. Oops, I kind of tilted that, didn't I? Well, I guess I'll have to fix it. There we go. We're left behind as a result of that inland sea. But that's what we see today. Okay, so those were areas where we could find all these threats of soil subsidence. How about effects of soil subsidence and soil volume change? What exactly do they do? Well, karst formation, of course, is where you have caverns underground that eventually result in sinkholes. And so if you have any kind of building over a sinkhole, it's going to result in the what's the word? The compromising of that sinkhole, or that ground. I'm sorry, the compromising of that building, which is on that ground, falling into that sinkhole. Groundwater conditions, all right, as caverns open up underground, they can change how groundwater flows. When permafrost melts, moving water even over the surface or even under the surface can change the structure of soil too. Coastal flooding and wetlands. So as areas get flooded by whether it's storms or rising sea level, wetlands all of a sudden they get destroyed because there's too much water. And when soil changes volume as a result of permafrost melting and then freezing, or frost heaving, all these can result in the soil itself changing volume and being a different shape than it originally was. Of course, with karst topography comes sinkhole formation, and wherever you have a cavern that's forming underground, chances are pretty good that a sinkhole could form, especially if the ceiling of that cavern collapses. Anything that is overlying that cavern where the sinkhole is can ultimately be compromised by that sinkhole. You'll notice that we mentioned Florida earlier, but also Pennsylvania as well. And actually, I'm going to go back to the slide of the U.S. Where are we here? Of the U.S. map. There we are. And you'll see that right here, I'm trying to move that around. Right here, that kind of green little arc through Pennsylvania, well, all the green stuff is really karst topography, but that arc especially is really the Route 30 corridor. That is that valley that Downingtown and Coatesville and Fraser and all those places reside in right there. So that green area is really karst, or I should really say just carbonate material underground. And since that carbonate is susceptible to acidic groundwater, it could actually be dissolved out and create caverns. So we could even possibly have some of that going on right in our backyard. So that's what I meant to refer to earlier. Sorry, I skipped that. So we'll go back. And we mentioned Florida already, but certainly Pennsylvania and anywhere else you see that green area on the map. Of course, right here are some examples of sinkholes taking place. I believe this one on the left actually was in Florida. Now that I look at it, well, it may or may not be, but they do happen often in Florida, and I'm pretty sure I thought I saw that recently in the news. Also over here as well, right? Sinkholes can swallow entire homes, all right? And so even if it doesn't swallow your whole home, it probably isn't a place you want to continue to live. So these become dangerous areas, especially if they've opened up into a sinkhole. All right, karst topography also results in groundwater conditions changing. If, like I said before, if you've got caverns opening up, all of a sudden water can flow somewhere else underground. So whereas you used to have a well from the surface down to the water table, maybe now you don't because the water table has dropped because caverns have opened up. It can also result in groundwater becoming polluted. having some sort of impurities added to it where previously it did not. If some cavern or even some crack or fracture opens up underground, it can allow other additives to be or other pollutants to be added to it that we didn't originally want. So right here is a stream. So this is where it's flowing kind of out of this cavern onto the surface right here. But in the same way, it can also flow from the surface into a cavern. And so where these karst areas open up underneath the Earth's surface, that can certainly redirect the flow of surface and groundwater accordingly. All right, damage caused by permafrost. Now remember, the name permafrost suggests that it's frozen year-round or frozen permanently, but every now and then when it does actually thaw, it can create damage. We know that when water freezes, it expands, and so when it thaws, it contracts, and so you can have roads caving in because they're no longer supported by that frozen ground. Runways fracturing, that's bad news because you don't want your planes hitting cracks and stuff on the runway. Railroad tracks can buckle because of changes in volume as a result of the freezing or thawing ground. And also building foundations cracking or tilting. All these can be a result of permafrost melting when we don't expect it to. Wetland loss is another hazard we can deal with. New Orleans and the Mississippi Delta, right? We know that's a very low-lying land, and there are a lot of wetlands and swamps around there. But when you have surges, storm surges that come from hurricanes and other storms, a lot of the swampland can either get washed away or subside. And so when that happens, it no longer can protect civilized areas like they currently do. And so that becomes a threat to humans as well. I know it doesn't sound very threatening, but soil volume change is one of the highest or most costly, expensive natural hazards that there is out there. It's probably not going to surprise you and hopefully not kill you, but it creates so much damage to structures that added up over the course of the year, it can exceed a lot of other natural hazards. So when soil changes volume, it can crack foundations. It can really mess with all kinds of objects underground. Like, let's say you've got underground water lines, or you've got water lines right here, objects under the ground. What about things like subway tunnels and that kind of thing? If you have the ground moving, even small amounts, anything that is in that ground underneath is likely to be shifted or otherwise disturbed. And so all these things added up can be very, very expensive to our country over the course of the year. Again, some of the effects that soil does that cause movement. You've got expansive soil. Remember, this is soil that as water is added to it, it expands. As water hits those clay particles, it expands. And so you can have houses that shift, and you've got utility poles that tilt one way or the other, or possibly roads or sidewalks that crack. Same thing with frost-susceptible soil. This is soil that cracks for another, or that expands for another reason, and that is not that water has been added, but that water that is in it is expanding because of freezing. So both of these things can cause the soil to change its volume, and as a result, man-made structures on and in the soil can really suffer damage. All right, so how are these soil subsidence hazards, how are they related to other natural hazards? Well, in many cases, they're actually the result of other hazards like earthquakes, volcanoes, and even climate change. I mean, as climate change takes place, you've got areas that are experiencing more drought than they normally do. All right, when areas dry out, they crack. We call them desiccation cracks. All right, and permafrost, which was areas of the earth that were previously permanently frozen and now no longer are because of climate change, that can cause ground subsidence as well. Not only that, but that water's got to go somewhere, and that can even contribute to sea level rise. So all those things can affect and cause soil subsidence. So soil subsidence itself can cause other kinds of hazards: flooding, of course, and mass wasting. We talked about how creep is a result of the ground moving very, very slowly. All right, well, as frost heaving takes place and soils swell up with water, then that means that the top layer of the soil can creep downhill, and that's when you would see those bent tree trunks and those tilted utility poles. And places where we actually are taking groundwater out faster than it's being replaced are likely to be susceptible to flooding because they are subsiding. They are actually lowering their elevation. There's places all over the country, and in fact, many of them are out west, that are actually lowering in elevation because we're pulling so much groundwater out. So these are some hazards that cause soil subsidence, and also some hazards that are caused by soil subsidence. All right, here's some desiccation cracks. Desiccation, of course, means when it becomes so dry that the particles can't stay together. They want to kind of contract, and so therefore cracks have to form in between the larger chunks of that soil. Okay, so are there any good things about soil subsidence? Well, in fact, there are. I'm just going to list these three right here: water supply, aesthetic and scientific resources, and unique ecosystems. And then what we'll do is we'll visit those in the next few slides right here. So water supply. Well, if you think about it for a second, karst areas, that is, areas that have lots of caverns underground because of carbonate rock being dissolved out because of acidic water, then there's all kinds of volume underground for water to exist. And so some of the greatest water supplies underground actually exist in karst regions. There's a giant aquifer in our Midwest that is at least partially there because it's a karst region. By the way, I should clarify, an aquifer is an area underground that contains groundwater. All right, so if you've got karst regions underground with caverns and caves, that creates a great place to be able to hold groundwater. How about aesthetic and scientific resources? All right, well, aesthetic means pleasing to the eye or beautiful. All right, well, caves in many cases can be beautiful. Some of you may have been to Crystal Cave out towards, I believe it's Kutztown, or other caves. Carlsbad Caverns, I think, is in Southern California. And so caves do attract visitors, and we see all those beautiful stalactites that hang down from the ceiling. And we see all those formations, those stalagmites that kind of stick up from the bottom, and all those features. So they're very nice actually to look at. Do they do anything for us? Well, not really, but well, at least not the aesthetic part of it, but they make our lives a little bit nicer just because there's something pretty to look at. They also have scientific value as well, because it enables scientists to be able to study some of these features underground, whereas underground normally is solid rock. If you're in a cave, you can walk right up to it underground if you're a scientist and study some of these processes. Also, some interesting ecosystems exist in these karst areas. There are animals called troglobites. Okay, and it might be a Y. No, I think it's an I. Troglobites. These are any animals that live in caves, and in many cases, these animals no longer have features that you need to be able to see with, because since caves are so dark, many of these animals actually lose these features. So in many cases of eyeless fish, other animals that don't even have any pigment to their skin because they don't need any pigment because there's no sunlight, there's no UV hitting them. So many of these types of animals, fish, shrimp, salamanders, flatworms, beetles, yes, you can see them at the surface, but they are also animals, very unique animals that can live in caves and therefore have some very interesting adaptations. Bats are another example. They're not completely troglobites because they do occasionally leave from time to time, but a lot of other animals are those that live in caves. So how about human interaction? Do we actually cause soil subsidence? Well, the answer is yes. In fact, we have something to do with a lot of these natural disasters. exacerbating them. This is just our list right here of the things that we do. And then we'll go into the more detail a little bit later. We draw subsurface fluids. That means like if you have a well and you draw water out, all right, well that water is no longer there. And so that's going to create some subsidence. We excavate underground mines. Frozen ground thaws, we're partially responsible for that. Deltaic, that is the adjective form of delta. So delta sedimentation, we restrict that. We'll talk about later as well. Surface drainage, we try to direct the flow of water across the surface. And just when we use bad landscaping practices in general, that can all contribute to soil volume change and subsidence. All right, so when we pull fluids out of the ground, it causes the rocks to subside. I mentioned groundwater before, all right, but natural gas is another one. Oil or petroleum, all these are fluids that we pull out of the ground. Now, when we mention things like mining, usually you think of mining as being like some sort of ore or something like that, like iron ore. But mining simply means taking something out of the ground at a faster rate than it can be replenished. And so when we mine groundwater, that means we're pulling it out in greater volumes than it's replenished, and so it's not able to recharge. So what you're essentially doing is you are creating a void, a cavern underground. And so the rocks that are above that are going to subside. This is what I was mentioning earlier about how out west land really subsides. This guy is standing at a pole right here, and it shows over the course of about 50 years how the land has subsided down. So that's what, about, I'm sorry, yeah, 50 years, about 50 feet it looks like. Right, so the ground level was up here at one point, and it subsided all the way down. Why is that? Well, Southern California needs a lot of irrigation, and as you pull water out of the ground for that, it causes the ground to subside. All right, so all these rock particles are separated by water when it's in them. By the way, this cross-section right here, this line of water represents what's called the water table, or we might call it an aquifer. All right, it's a water table. The aquifer is actually the rock that the water can percolate through. All right, now bedrock down here is impervious to water, and so the water doesn't seep into that. But this aquifer, that is the soil or whatever rock particles the water can flow through, exists up here. And this is the water table, and as long as you get a well down below the water table, you can draw water out. But if you draw too much water out, like over here, these particles can settle together, and since there's spaces in between the particles now, the water is no longer there. They settle together, and we see up here the level of the ground actually subsides. Excuse me. And so that's what's actually happening in Southern California. All right, when we mine underground, one of the processes that we use is we shoot water underground and we blast out rock, and then we use water to pump out the resources that we want. In some cases it's salt, other cases it's other minerals. All right, but this is a very damaging type of mining, how you just sort of use water to blast out rock underground. And then once it's blasted out, what do you do with it? Do you fill it back in? Most mines are not filled back in. And so they, in many cases, they flood them. They flood them so nobody will fall into it. And so you just have this very, very deep mine with water filling up. So this can be very damaging to the environment. It's just the left behind of mining. All right, we're also partially responsible for melting permafrost. I think we're all pretty much on the same page that at least to some degree we have some effect in global warming. All right, and so that can cause permafrost to melt. If you've got buildings that generally have heat in them during the winter, if the heat can't be removed from underneath buildings, it can cause permafrost to melt as well. Also, utility lines. Many places where you don't see above ground power lines, it's because they're buried underground. And so those utility lines carrying electricity can heat up. That can also cause permafrost to melt as well. So we know the problems that melting permafrost poses, and this is some of the things that we do to cause permafrost to actually melt. Okay, we know that sedimentation in deltas, when that sedimentation builds up, that's good because the ground is being built up. But if we reduce that, if we restrict the sedimentation, obviously it can't be built up. So why do we, or what do we do to restrict it? Well, we create dams upstream, and so of course that restricts sediment from coming downstream. We build levees, all right, and so what that does is that channels the sediment away from where we want it to go. And so also where we have river water and we don't want it to be full of all that sediment, it just seems like muddy and gross, oh yuck. So we just divert it into canals where we can do something with the sediment. That prevents it from being able to come downstream and build up areas around deltas that need to be built up. So that's another thing that humans do to restrict sedimentation or restrict the buildup of sediment around around deltas. All right, we're also really notorious for altering surface drainage. That is, if there's a river or a stream or something that is inconvenient to us, we oftentimes can redirect that. We create man-made canals and streams and stuff. We also tend to do that for agriculture as well. You know, as we create irrigation canals, we're essentially creating man-made drainages. And so when we do that, the water can't go where it naturally wants to go, and so it can show its effect on the soils. Collapsible soils collapse, expansive soils expand because of water being added. So these are some of the things that we can do, that humans do, that actually cause the soils to fail and subside as a result of surface drainage. We can even do some things that seem harmless, but that can also have an adverse effect on the soil. Landscaping. I mean, it seems like landscaping is an occupation that is very natural and friendly to the environment, but if it's done poorly, it can, like I said before, it can have an adverse effect on the soil. Like if you plant trees and shrubs too close to foundations, what that can do is that can pull moisture out of the ground, and so the soil won't have anything really to work with. Soil can shrink, it can crack as a result of that. Many times we plant grass and garden crops that need frequent watering, and so you've got to bring in more water than would naturally exist right there. So these are some of the things that we can do as humans, just even in and around our houses, that can contribute to soil failure and soil subsidence simply by using poor landscaping practices. All right, so what can we do to prevent some of these hazards, these soil-related hazards? Well, we can reduce fluid withdrawal. That is, we can restrict how much oil and water gets pumped out of the ground at a certain time. We can regulate mining. All right, not just give anybody the go-ahead to mine, but do it in areas where it's going to have the least impact on people and the environment. Also, reduce damage from thawing permafrost. What we can do is we can build buildings on adjustable screw jacks, and so we can raise them up to the point where the heat from the building is not going to cause permafrost to melt. Also, certain types of foundations can allow freezing and thawing to happen naturally without affecting the foundation itself. All right, we can also reduce damage from the subsidence of delta sediments we can actually allow controlled flooding. We talked about that in the flooding chapter, how sometimes controlled flooding can actually build up places that need sediment, and marshes need sediment so they don't drown in the coastal waters. We can limit irrigation. All right, so that prevents organic and collapsible soils from being over-drained or under-drained. All right, so we can manage irrigation a little bit better. Even in and around our homes, if we manage the draining of water in and around our properties, we can prevent damage to our own homes because of either too much or too little water being on our properties. Water trying to get into our basement and into our foundation, or not enough water being near the house and so causing the soil to crack. So all these things are things that we can do as humans to reduce those factors. Well, part of the problem with us as humans is the fact that many people have a very weak perception of the threat of soil subsidence. If you're honest with yourself, you probably don't think of that as being one of the biggest, terrifying natural hazards out there, but it is very widespread. So there's very little media coverage about it, and so it doesn't get a whole lot of press, and people aren't made aware. People do need to be made aware, and so they can take precautions and measures to prevent these kinds of natural hazards from happening. It's really people who live in the areas like this that are the most aware, and they really do see it as a threat. I do know people in Florida where sinkholes are common. Many people are very aware of that and take as many precautions as they can. But outside of that area, you probably don't hear a whole lot of awareness about that kind of threat. What can you do to prevent subsidence and soil volume change? Well, you can map the soil. All right, you can geologically map it, and so if you're going to build something, you'll know exactly what kind of hazards are there, and so you can kind of manage your risk that way. Any kind of features you see on the surface, like cracks, should be noted, and they should be kind of followed up on to see if it's a sign of anything more insidious. And when you're building in any kind of karst region, you want to be able to survey the ground under your feet. We have ground penetrating radar that can do that. That can determine what kind of materials are underground and how susceptible they are to soil subsidence. So here we are back to the very beginning. We talked about Venice at the very beginning, and so we're going to see how we can apply the concepts of hazard management to Venice. All right, so we talked about how it's made of hundreds of small little islands, and it's been that way for years, and a lot of the structures are built on wooden piles or pilings that are driven into the lagoon floor. It's really the records that people have kept over hundreds of years that have really helped the Venetians to be able to predict and kind of manage how fast the city is sinking. As we mentioned, flooding is just a perennial problem, and people walking through the streets just kind of slogging through water. It's just kind of a way of life, but it can be managed. Some of the management schemes they've come up with is actually jacking buildings up, having them built on jacks so they rise a little bit. But part of the problem is really, well, the big problem is the human impact on it. More people than ever live in Venice than ever did, and so you've got more and more people pumping out groundwater. People need groundwater to live, obviously, and so as you pump groundwater out from underneath the aquifers, under the lagoon, it's going to subside. As a result, the lagoon waters rose by more than 2 meters. That's about 6 feet. All right, and so as we continue to pump water out from underneath, the city of Venice keeps sinking, and it really is not stabilized. It was once believed that it was stabilized and kind of evened out a little bit, but it continues. The city of Venice continues to sink into the lagoon floor. There is a project called the Moses Project that was to the tune of about $7 billion. That was very controversial, and what it did was it managed the flow, or it's proposed to manage the flow of water in and out of the area of the city of Venice by way of giant locks. And I'll show you that in the next and final slide in just a second right here. But the problem is it won't really put an end to the flooding. All right, so this is the Moses Project. And so you've got these walls, these seawalls right here that can be raised or lowered. And I think water can even kind of flow, can be allowed to flow kind of into these locks right here. They're kind of hollow. And so as water goes in, the air that is trapped in them causes these seawalls to rise up and block more water from coming in. And so as the sea level rises, it can cause this wall to rise up even further, blocking more seawater. But the problem is it really isn't a long-term solution. It's a solution that prevents large amounts of water from coming in, but the difficulty is that Venice continues to sink, and unless some of these problems are addressed, they're going to have an even bigger problem on their hand, that is the city itself sinking into the lagoon floor. So that is our chapter on soil and subsidence. I thank you for bearing with me. This was the longest section, even though I think we got through all these slides pretty quickly. And I will ask you, if you have any questions, to make sure you please come and see me, and we'll clarify them. So in the meantime, I do thank you for watching, and I'll see you on the next one.